I'm going to show in this video how to solve the example problem on Fogler problem 10-12 using PolymathPlus. So I've navigated to the PolymathPlus website. I'm going to log in using my account information that I've already created. When I get there, I'm going to click on Solver. The solver takes me to a place where I can enter in text. That's going to be right here. I can go ahead and enter in text. I'll do that in just a minute. Another thing that you can see here is there's different example problems. So there's different ways, for example, of solving linear equations, nonlinear equations, differential equations. Differential equations is what we'll solve here. You'll see there's a couple different ways of syntax that we can do that. The one that I'm going to choose is kind of analogous to this one because I think visually it makes the most sense, but just so you're aware, there's multiple ways you can do this. I'm actually going to delete the code that's here, and I'm going to enter in my own code. If you are not comfortable with coding or with using mathematical software, I do not recommend that you do that. I recommend that you take existing code and modify it because it decreases in that way you don't need to know all of the different ways of syntax. You can simply modify syntax that has already worked for solving some problem. So I'm going to go in here and type this in to show you how it's done. So the ODE that I want to solve is the PFR mole balance. That's in the form dx dv. In the syntax structure that I'm using here, I'm going to indicate my variables using parentheses. So I'm going to put both x and v in parentheses. I'm going to write out then my mole balance symbolically. The mole balance is equal to minus RA divided by FA naught. Now I need to go and define those things. So RA, I'm going to write an equation for. I want to write an equation for RA and not minus RA. We use the minus RA to indicate a rate of consumption. Mathematical software does not know that, so I'm going to write it as a rate of generation and then make the rate of generation for A be negative. That's going to be K, or negative K times the partial pressure of A squared divided by this denominator term, got KA times PA plus KB times PB, and that is squared. Okay, so now I need to enter in my constants. I have K is equal to 1250, KA is equal to 4, KB is equal to 13. I now need to enter in my equations for PA and PB. So PA is going to be equal to PA naught times 1 minus x divided by 1 minus x divided by 2. And then PB is going to be equal to 0.5 times PA naught times x divided by 1 minus x divided by 2. All right, so I still have a couple of variables I need to enter. So for example, if I click solve, I'm going to get some errors. That's because I don't have enough variables assigned. We see I'm missing information on how to integrate. I'll show you how to do that in a second. I'm also missing information for FA naught and PA naught, so I've got to enter that. So FA naught is equal to 2, PA naught is also equal to 2. Now if I were to click to solve, I'll reduce my number of errors, but still I haven't told the solver how to solve the problem, so I'm going to do that next. I'm going to say my initial value of x is equal to 0. I'm going to say my initial value of v is equal to 0. And then finally what I want is my final value of v. I'm going to indicate that with a lowercase f. And I'm going to say that's equal to 2. So now I should be able to solve. So I'm going to click solve, and there you go. So I click solve and I get an answer. These are the variables that, or the values that the software is calculating. It's going to calculate everything that we've entered as a function of x. It's going to calculate that as a function of x, and it's going to summarize the data here. So it's told us that our initial value for the partial pressure of A is 2. our initial value for the partial pressure of B is 0. And then what's happening is A is decreasing over time, gets to a minimum value of about 0.13, while B is increasing over time and gets to a maximum value of about 1.8 or 1.9. We also have the rate as a function of x, and so those values are here. We have our volume and our x values. We see the plot here is going to be x versus v, or so the conversion versus the volume. We see that at 2 liters, we're going to get our final value of conversion is going to be 0.97.